to our session on decoders, another form of combinational logic that's useful in a variety of digital logic circuits. A decoder does the opposite of a multiplexer. The decoder places a 1 or a high input onto one of many output lines, and those one of many output lines are dictated by the input which act in a similar way to the address lines into a multiplexer. So in this example of a 3x8 decoder, the three inputs basically select which of the 8 possible outputs will go to 1. For example, if A is equal to 1, B is equal to 0, and C is equal to 0, then the D4 output will go to a value of 1, and all the other outputs will go to 0. And in another example, if A is equal to 1, B is equal to 1, and C is equal to 0, then D6 will go to 1, and all other outputs will be equal to 0. So D0 through D5 and D7 will remain at 0. So the decoder essentially takes a binary encoded input and puts it onto output lines in a scenario or a situation where only one of the output lines will be 1. The 3x8 decoder and many other decoders can be implemented in one of two different ways. This is the straightforward decoder and involves putting a 1 onto one of 8 output lines depending on what the select or input lines are doing. This is a situation that we discussed in the previous slide, and it results in one of the outputs of the decoder always being equal to 1. One and only one of the outputs of the decoder are equal to 1. Now sometimes it may be advantageous to be able to set or reset all the outputs of the decoder to 0. And we can do that using an enable bit. And when that enable bit is high, the decoder works as normal. And this is exactly identical to what we had on the previous slide for the 3x8 decoder. When enable goes low, though, the decoder ceases to function, and all of the outputs D0 through D7 go to 0. The enable line simply gives us another option in what's going to happen with the outputs. Now, just like with the multiplexer, we can implement rather large decoders using much smaller decoders. In this example, we'll implement a 4x16 decoder using 2x4 decoders. And in this first decoder, 2x4 decoder, 2 inputs by 4 outputs, what we have is the most significant bits on the inputs, select 3 and select 2, will create 4 possible enable signals. So if select 3 and select 2 are equal to 1, 1, then enable 3 will go high, and the remaining enable bits, enable 0, enable 1, and enable 2, will all be equal to 0, and so on and so forth. So the function of the first decoder is simply to activate one enable signal that will be used in subsequent decoders to implement the entire 4x16 decoder. So let's take a look at what that looks like. Here we have our first phase, our first stage of the 4x16 decoder that's selecting one of 4 enable lines. And subsequent 2x4 decoders will then select which of the 4 outputs in that block of 4, in this case when enable 0 controls the first 4 outputs of the decoder, out 0 through out 3. When enable is high, as selected in the first stage, then select 1 and select 0 are free to do their jobs, and select one of out 0 through out 3 to be 1. And we can do the same with 3 other decoders, and each decoder in the second stage of logic is powered or enabled by one of the 4 enable signals that was produced in the first 2x4 decoder in this design. In this way, we can build decoders that are as large as we like using much small decoders as building blocks. We can also use decoders to implement combinational logic if we need to. In this example, we're going to go ahead and implement a function wxz or yz0 with a 4x16 decoder. To do that, let's first take a look at the truth table for f that results from these two terms. When w, x, and z are all 1, the output f will be equal to 1. And that occurs here. W, x, and z are all equal to 1. And it also occurs w, x, and z all equal to 1 down here. So this first term takes care of these two lines in the truth table and ensures that the output f is 1 in these two situations. Now we also know, according to the logic shown here, that when y is equal to 1 and z is equal to 0, the function f will also be equal to 1. And that occurs in this line where y is equal to 1 and z is equal to 0. It occurs here, producing an f value of 1, and also here, as well as down here in the 15th line of the truth table. So to implement this using a 4x16 decoder is fairly straightforward, because w, x, y, and z now will just serve as the inputs to the 4x16 decoder. And using that, we can then implement the 4x16 decoder by taking a look at when the outputs of the third line of the truth table, the 7th line, 11th line, 14th, 15th, and 16th line, that's when we want the function f to be equal to 1. So we know that these address lines, if we use w, x, y, and z as the inputs to a decoder, that when w is equal to 0, x is equal to 0, y is equal to 1, and z is equal to 0, we know the corresponding output for the decoder, out 2 in this case, will be equal to 1. So we can just OR everything together to come up with the final expression. So to come up with the implementation of this using a decoder, in this case a 4x16 decoder, we have 4 inputs, w, x, y, and z, that are just selecting one of these 16 outputs to be equal to 1. And of those 16 outputs, we know a few of them will be equal to 1 when we want them to in order to implement f. So in this case, the function f will just take a few of the outputs of the decoder and OR them together. We'll take out 2, which corresponds to this third line of the truth table, or out 6, or out 10, or out 13, or out 14, or out 15. And when we implement f as an OR gate of these several outputs of the decoder, we'll essentially have implemented f using the decoder approach. Now there are other ways, of course, to implement combinational logic functions using decoders. In this next example, we'll use a different technique. We'll take a look again at calculating the output f given the input variables a, b, c, and d. And as we fill out this truth table, given these many terms in the input, we'll discover that there's only one scenario in which we get an output of 0. So in that case, it's pretty straightforward. F is then essentially equal to this 14th output, its inverse. And what that tells us is that when A, B, C, and D are equal to 1, 1, 1, 0 respectively, the output 14 will be 1, and if we take the inverse of that, we'll get 0, which ultimately implements the function f as expressed here in a more complicated Boolean form in the problem statement. Using decoders to implement logic functions is more straightforward than for multiplexers, but the logic involved and the number of gates and real estate involved in implementing a decoder can be quite large as well, so they're not always used as much as multiplexers to implement combinational logic. But they're useful for a wide variety of other functions when it's important that we convert what is essentially a binary number to a different sort of code here at the output, where only one output is 1 at a time. So these decoders distribute 1 to many rather than selecting 1 from many, as is the case with multiplexers. They can be used to essentially decode a binary number by setting only a single output to 1, and they can also be used to implement combinational logic in similar ways to the way multiplexers do. Well, that's all for decoders today. Thanks for joining us as we continue to explore the world of digital logic and circuits, and we hope you'll join us again soon.